Okay, hello everyone. Let's get started. So for today's class, we're going to be continuing sorting algorithms where we left off from last time. So if you remember, last time we introduced the concept of sorting and time complexity, and we went over one simple sorting algorithm, which is bubble sort. Today, we're going to explore two other kinds of sorting algorithms called selection sort and insertion sort. And first, I'll go over what those are and how they work, and then we will write the code for it ourselves. Um, so let's first talk about the first one, which is selection sort. So how selection sort works is that it's a simple comparison-based sorting algorithm. Just like bubble sort, we're going to be comparing items. And the premise of it is that we're going to divide the array into two parts. So on the left side, we are going to have a sorted part, and on the right side, we have an unsorted part. So yeah, next, the algorithm will repeatedly select the smallest element from the unsorted part, so the right side of the list, and it will swap with the leftmost unsorted element. And I'll show a visual of this in a second. And this algorithm, just like bubble sort, has a time complexity of O(n) squared. But this is for all cases, so worst case, average case, and best case. And it is an in-place sorting algorithm, so it does not take up any extra space. Okay, so let's go over to Wikipedia, which always has really nice animations for these algorithms. And let me see if I can replay it. So this animation plays kind of fast, but what it's saying is that the yellow part is the sorted part, and then everything under that is the unsorted part. And the red one is the current minimum, and the blue one is the current item. So I know this is kind of fast to see. And this is also, it's vertically instead of horizontally, which also kind of makes it harder to visualize. But in this case, the top part is the sorted and the bottom part is the unsorted. Let me see if I can find another animation. Okay. Okay, I haven't seen this one before, but so for example, right here, 3 is already in its sorted position. So 3 is part of the sorted half of the list, while everything on the right here is unsorted. So as you can see, the algorithm found that 5 is the minimum value, and 80 is the first element in the in the unsorted part of the list. So it will swap 5 and 80. So it will make that swap. And then after that, so 3 and 5 are already sorted. We will find the next minimum value in the unsorted, so the white part of the list. And I think that would be 7. So it will identify 7 as the minimum value, and it will swap with 62. So now 3, 5, and 7 are sorted. So the next step is to swap 8 and 67. So it says 8 is the minimum value, and the first value in the unsorted sublist is 67. So we will go ahead and swap them. And then it will keep doing that. so on and so forth. So by the end, everything that's green will be sorted, and then everything on that side is unsorted. So it will keep on making those swaps. Okay, does anyone have any questions on how this works? Okay, if not, then let's talk about the code. So for each round, we have to go through all of the items and find the smallest remaining item. And each round, it will swap it with the first unsorted item. And after n-1 passes, we should have a fully sorted list. Okay, so let's go ahead and create a function called selection sort. And then we can pass in our list of items. So we have to make a total of n passes. So for I in range, so the length of the list is n. So that's where we get n passes. And for each pass, we have to search for the smallest item. So let's keep track of an index for the minimum item. Let's call it min index. And since we don't know what the minimum value is at the start of the pass, we can, for now, let's set it to I. So this is the index for minimum value, for minimum item. For the inner loop, we can start from I plus 1 to the end of the list. So we're taking advantage of the fact that every pass, we have exactly one more item that will be that will be added to the sorted sublist. So for the unsorted sublist, that will start from I plus 1 and go to the end. So you can think of it as everything from index 0 to I is part of the sorted sublist, and everything from I plus 1 to the end of the list is the unsorted part. For the inner loop, all we have to do is compare the current item to the minimum item we found so far. And if the current item is even smaller than the minimum item, then we can set the minimum item to the current item. So to make that comparison, let's do items J, so that's the current item. If it's less than the minimum item, so the item at the minimum index, then let's set the minimum index to J. So here we have to be careful that the logic for the if statement is the actual item. So we have to do the list sub index, while for this one, we're just setting the index. So we don't need to reference the list here. After the inner loop, we should have found the smallest item. And now we have to swap the smallest item and the first item in the unsorted sublist. So that item would be item sub I, and then we are swapping it with the item at the min index. So now we have made that swap. Does anyone have any questions? Okay, if not, then we are done with this function. So we can return the list at the end. Or actually, we don't have to do that because we're sorting it in place. So now let's go ahead and create a random list that we'll use to sort. So let's say we have 1, 5, 4, 2, 6, 8, 3. And let's go ahead and call the function. Call it nums. Okay. So as you can see, it's now sorted. Just like last week, we're also going to uh, examine the time complexity in a bit more detail to help you understand this algorithm. So, but you don't have to write down the code for this since it's not part of the algorithm itself. But let's import time so we can time how long it takes to sort the algorithm for different sizes of lists. And then once again, you don't have to write out this code. Okay, where did I do? Okay, so I generated a bunch of random lists, and these are the length of the list on the left, and then here we have the time it took to sort the list in seconds. So now let's go ahead and plot this. So you can see, just like bubble sort, this has a upward increasing curve, which tells us that as the sample size increases, the time is increasing by n squared. So why is this algorithm O(n) squared? That's because our outer loop runs a total of n times, and the inner loop runs n minus I times. So in total, we're making n times n minus 1 over 2 comparisons. So that equates to O(n) squared. And this is always the case regardless of the list because we're always performing full scans, unlike bubble sort. If you remember in bubble sort, once the list is already sorted, we have a mechanism that allows us to break early and end the sorting right there instead of making unnecessary comparisons. But for a selection sort, that is not the case since we are always going to be making n passes. Since each pass, we can only guarantee that the first I minus 1 elements are fully sorted. Some other key differences between bubble sort and insertion sort is that I mean selection sort, and selection sort is that selection sort has to make at most n minus 1 swaps. So one swap per pass. And this is going to be convenient for us if for some reason swapping is expensive. So it's either it for some reason that it's just we just want to avoid making swaps. Whereas bubble sort can require up to n squared swaps in the worst case. So that's considerably worse than selection sort. I mentioned this just then, but in terms of adaptivity, bubble sort is more adaptive since we can terminate the sorting early if it's sorted, but selection sort always has to scan the entire array. So when should we use bubble sort and when should we use selection sort? So both of these algorithms are by far not even close to being the best sorting algorithms. So usually we don't use these at all because we have more advanced algorithms that are faster. But if we are deciding between these two algorithms, selection sort is going to be better if we want to try to limit the number of swaps and also when our data set is relatively small. And we want to use bubble sort in the case that our data is almost already sorted. So we call this nearly sorted. And also if we want to terminate early. And then another point about the stability is that when we say stable, we are referring to duplicate numbers. So that means for bubble sort, if we have two of the same numbers, we actually don't make the swap. So it will preserve that order, which means it's stable, whereas selection sort may change the order of duplicate numbers. But that isn't a super relevant fact that we care too much about. Okay, any questions before we move on to the next sorting algorithm? Let's move on to insertion sort. So this is yet another simple comparison-based sorting algorithm. And this one works by building the final sorted array one element at a time. So we can make an analogy for sorting playing cards. For example, if you've ever played any card game before. So you can think of it as, let's say we have a deck of unsorted cards. If you were to sort this deck using insertion sort, you would take one card at a time. So let's first take one card, and that card by itself is going to be already sorted. And let's take another card from the pile, and then we're going to sort those two cards. So now we have two cards sorted, and let's take a third card from the pile, and we're going to sort those three cards. And then once we have those three cards sorted, let's take a fourth card and then sort those four cards. So each time we're taking one more additional card from the unsorted pile, and we're going to make sure that the cards we have in our hands, we're going to sort them. So that's kind of how it works. The insertion sort algorithm has an O(n) squared time complexity for the worst case and O(n) for the best case, which is nearly sorted data. And this algorithm is stable, which means it will maintain the relative order of equal elements, and it's also an in-place sorting algorithm. And I'll try to find an animation once again. Okay, this one is kind of fast and it's sorting by height. Okay, let's do this one. So 6, so now we add one item, 5, and we have to make a swap. So now 3 is the next item, and we will sort the first 3 items. So as you can see, each time we are bringing in an additional item and sorting that item into place. So the items in the black boxes, those are already sorted, and everything to the right of that is unsorted. So a key difference between this one and between insertion sort and selection sort is that selection sort in the unsorted partition, we are finding the smallest one, whereas this one, we're not finding the smallest one, we're just getting the next item and then sorting it into place. Okay, I'll play the animation one more time so you have some time to visualize it. What do you mean by math equations? Okay, if I were to use multiplication or division and sort that in a list, would the code you made work with this? Are you talking about like sorting the operations? So the results of operations. So that okay. So yeah, so as long as it's numbers, this sorting algorithm will work, and it will also work for like strings as well. But the code we're writing only applies to numbers. So yeah, in some cases you may be doing like some math operations on numbers and then sorting the results of those. So generally, I would imagine that you would be doing those operations first, and then once you get the results, you can directly use one of these sorting algorithms and it will sort them in order. Does that answer your question? Okay, great. So let's talk about insertion sort. Okay, let's make a function called insertion sort. So each time we are inserting one new item into the current items that we are dealing with. So in the first pass, we only have one item and it's already sorted. So we can actually just start from the second item. So we can start from index 1 and then go to the end. So that basically means when we have already one item by itself, we don't have to do anything. So we can go ahead and start with the second item. So we can start from inserting the second item. So we know that everything in the sorted section of the list, so on the left side, is already going to be in order. So the task becomes, so we have this new item. We want to figure out where the new item should go in that unsorted, in that sorted portion. So if you look at the animation again, oh, it's not this one. Where did it go? Oops. So every time we get the newest item, we have to compare it with the previous item. And if it's not in the right place, we have to swap. So for example, 1, we should first compare it with 6, and then we compare it with 5, and then we compare it with 3, and then we swap. So with 8, it's already in place, so we can move on to 7. And 7 and 8, we compare them and we swap them. So what it's doing is, so in this case, 2 and 8, we swap them. 2 and 7, we swap them. 2 and 6, we swap them. 2 and 5, we swap them. And then 2 and 3, we swap them. So we have to keep swapping until it's in the correct position. So we can set our current index to I. So in the beginning, I is going to be the position of the new item that we are inserting. And as you can see in the animation, we're actually working backwards. So our inner loop should be going backwards. And we don't know exactly when to stop for sure. So in this case, a while loop will be more convenient than a for loop. So the condition should be, first of all, we have to make sure that our index is greater than 0, right? Because if it's equal to 0, then that means it's the smallest item and we should swap it until we get to the smallest item. And also we will keep swapping when the previous item is greater than the current item. So this is the condition for our while loop. Um, okay, let me go back to the animation. So 5 is the current one. So while the previous one, which was 6, is greater than the current one, we should swap. So 3 and 6, since the previous one is greater than the current one, we should swap them. So as long as the previous item is greater than the current item, we need to make the swap because the previous item should be less. And let's write the logic for the swap. So current minus 1 and current are the items that need to be swapped. And since we are using a while loop, we need to subtract our index by 1. Okay, and we are done. So once again, I'm going to keep track of the time here, which you don't have to do. Okay, does anyone have any questions on how this code works? Okay, if no questions, then let's try this function out. Okay, so let's create a random list of numbers and then call the function. And as you can see, everything is in increasing order now. And like before, let's generate a whole bunch of random lists and see how the performance fares. So we also get this familiar curve. So for the time complexity of the insertion sort algorithm, the best case is just ON, since we are not actually making any swaps. And that the reason for that is because the while, if it's already sorted, the while condition would not be satisfied. So we actually just don't end up doing any of the code inside the inner loop. So it's essentially only the outer loop. So that's why it's ON for the best case. And for the worst and average case scenarios, we're going to have to make some swaps. So that's we're going to be dealing with the inner loop as well. So the time complexity would be ON squared. And in the worst case, this one's kind of easy to talk about. So each element is being compared with all the previous elements in the worst case scenario. Worst case just means the array is completely in reversed order. And an average case typically will require n squared over 4 comparisons, but we still say that's ON squared. So now that we've talked about the three most simple sorting algorithms, let's compare them and see some of their advantages. So over here, I have insertion sort, selection sort, bubble sort, and quick sort, which we haven't learned. Quick sort is one of the fastest sorting algorithms and one of the common ones that we actually use. It's good for general purpose um, data sets, and it is ON log n. So that's the best one out of these four. Bubble sort is typically only used, is good for educational purposes, which is what we are doing now. And insertion sort and selection sort will have their good use cases for small and nearly sorted data sets. And insertion sort will outperform bubble sort and selection sort on very small data sets, so like less than 10 in size, and also nearly sorted data. So we can actually do a comparison between the three algorithms we've learned as well. Let's draw a plot. You don't have to do this, but let's look at a plot of the running times of all three of them at the same time. So, let's see if I have some problems. Okay, we need to find it. Let's go ahead and define our previous algorithms. It's taking some time to run. Okay, so we have a plot over here. So as you can see, um, bubble sort typically will suffer from larger lists, and selection sort is in this case it was the faster one of the three for the larger lists, and insertion sort was somewhere in the middle. Uh, okay, let me run this again. Okay. Okay, so I think you can ignore these peaks over here. I think that's just the server probably had too many requests and it slowed down a bit. But yeah, generally bubble sort is not very ideal for large lists. And then finally, let's take a look at how these three algorithms compare for nearly sorted data. Okay, so for the nearly sorted data, bubble sort also takes very long. And in this case, insertion sort performed the best. So I think insertion sort and selection sort, sometimes one will be faster than the other because I've done this demo in the past, and I think selection sort was better on this one, but in this case, insertion sort was better. So yeah, insertion sort will generally be better for nearly sorted data. Okay, does anyone have any questions? Yeah, and the reason insertion sort is generally the best for nearly sorted data, it's because when the data is nearly sorted and we insert a new item, we don't have to make that many swaps, maybe one or two at most. So the while loop inside will break early. Yeah, so it becomes ON in that case. Any questions? If not, then we'll end a little bit early today. So yeah, thank you everyone for coming today, and stay behind if you have any questions. And I'll also try to post all the code on GitHub after class today. Okay, thank you everyone.